Hello, everyone, and welcome to The Current, the North Central Region Water Network's Speed Networking webinar series. The North Central Region Water Network is an extension-led collaboration among land-grant universities in 12 upper Midwestern states, and I am Rebecca Power. I will be your moderator for the day. March 22nd is World Water Day. This year's theme is wastewater. To help us highlight that theme, we have two presenters that are highlighting university and university extension efforts to help manage on-site septic systems. Our presenters today are Dave Gustafson from the University of Minnesota and Steve Safferman from Michigan State University. Janice, if you could just back that up for a minute. I know I'm going a little bit out of order, but so we'll be hearing from them in a minute. For those of you joining us as participants, you will be able to submit your questions in the chat box for presenters. That chat box should be on the lower left-hand side of your screen. We will have a dedicated question and answer session after our two speakers are finished, and I'll be moderating those questions and getting them to the presenters. So we should have a good amount of time for questions at the end. Okay, so our presenters, Dave Gustafson and Steve Safferman. Dave is going to be covering Minnesota's perspective on connecting system owners to system performance, and Steve Safferman is going to be talking about phosphorus and on-site wastewater pollutant to resource. Two exciting topics. And we're going to start out with Dave Gustafson. So his bio is here. We're not going to read through those, but you can glance through that and see his great shot there. And we are going to hear from him starting now. So Dave,
welcome, and thank you so much for inviting me to talk. I actually have that same sweater on today, so that's kind of fun. And for those of you that haven't met me, and the bio went too fast, this is my 27th year working here at the university, doing the education program for professionals here in Minnesota and in other places. More importantly, though, I am the father of 6 daughters, and so that they've given me all kinds of experience as a person to understand what you can do to cause systems problems, and more importantly, how to communicate with problem users. So let me introduce you just a little bit to Minnesota. So our Minnesota code is Chapter 7080 that lays out system standards. So that defines what systems look like, how systems go in, and expects good performance out of those systems. And our definition of good performance is making sure that the wastewater is treated before it's recycled, and we spend a lot of time working on those kind of performance indicators with the professionals. We also license all of the professionals in Minnesota. So you can see there's a list of designers, installers, maintainers, and all of the local county inspectors also need to go through our education program, but more importantly then, have the same background and basis of decision making for what makes a good system and what makes a system fall into the problem category. That education program has been active here in Minnesota since 1996 in terms of licensing, and it is always, to me, improving. In particular, now we're updating all of our exams to better kind of prepare people, or better understand where people are at in terms of that preparation. The other big thing in the Minnesota Code is the second point there, which is system care. And our code has done a number of things to allow systems to be better cared for. One of the big things in terms of system standards is including access to the tanks and other technologies for care. And then there are 2 specific components to the code to help make sure that the systems are dealt with. The first is what's called a management plan. And the management plan is the one part of the code that all of the professionals have a component or piece in. The management plan is written by the designer and lays out for the system what needs to happen in terms of care and what the owner's responsibility is in terms of care for the system. That care would include the activities of care and the frequency or how often that should happen. That then is submitted to the county or the inspector that reviews it and approves it and places it in the system file. So the management plan is in a long-term record. The management plan is then delivered by the installer to the owner and then followed by the maintainer. So all of the licensed professionals interact with the system via or through the management plan component. And what I really like about that is that the management plan is in our Minnesota code requiring it for all new systems. And I'm going to say it went into the code in about 2007. So some of the more thoughtful counties and regulatory groups have instituted at time of system transfer or property transfer that the inspector would update or replace or create a management plan. The second level of system care is for additional technologies. So if my system needs some additional technology like an aerobic treatment unit or a media filter or a UV to lower the bacteria counts, those technologies are required to have an operating permit as part of the system approval. The operating permit is a document that creates a relationship between the system owner and the regulatory group. In the operating permit, the activities of the management plan are identified, as well as a reporting requirement of flow and other indicators of performance. And those have been pretty successful here in Minnesota. They don't get applied to what I would call conventional systems, septic tanks followed by a soil treatment area, if that system is full size. But if I have an existing property that is not full size, the local units of government can use those operating permits as a tool to make sure that they are worked on or regulated or overseen to make sure that the performance is happening. So that's kind of a background in terms of Minnesota. I'm going to introduce and talk about two different projects that we've worked on here at the university. The first project was up in northern Minnesota in our lake country, so I just included a little map there showing the Alexandria area. The county, Douglas County, is interesting in that it has some really fantastic lakes. And those lakes are kind of broken into two categories. The lakes in and around Alexandria are actually serviced by a municipal system, so they have city sewer. And then the other lakes are serviced in terms of their wastewater infrastructure with on-site systems. At the beginning of the project, some of those lakes were looking at moving to municipal and were voted down because of the cost of that municipal system. So instead, the county wanted to look at a way to better identify systems at risk, to look at ways that they could prioritize where they would review systems, and then a method to keep track of those. So we went through and worked with them and developed a plan that put the system, the user, and the site into a hopper to identify kind of the risk of the area and the system, and then allowed the county to decide two things. Number one, where in the county they needed to do some information gathering or inventories, and then how those systems would be long-term cared for in terms of management. And so what we ended up with was a review of the technology that sets the minimum of maintenance. And that's one of the things to me in terms of systems that we're seeing is a change that originally, I'm going to say we had relatively straightforward technologies where we were using gravity in the soil. Now we're finding that some of the places we want to live, some of the planning decisions, we need some additional technology to make those systems work and operate. So from the design that sets the minimum in terms of maintenance, and when I say minimum, I mean two things. The actual care, and then more importantly, how often I'm there dealing with it. And that's one of the things that I see missing in a lot of the thoughts of management, and that is that people understand they need to take care of their systems, but don't understand that based on the site and the user, that care needs to change. The tool then takes and evaluates the risk and the user to better create or to better update that. Along with that, the county added access database that allows them to track all of their systems in terms of overall use in the county. The second thing that we ended up with was information things, and I actually brought a copy of our homeowner's guide here, but you're not going to get to see it. That's the extension tool that allows us to communicate how to take care of systems. You see here the local brochure that we developed to allow them to better connect with systems there in Douglas County. And the last part was what I'm going to call an individual O&M. And so that's the next tool or the next project, which was H2O&M. And H2O&M is a tool like TurboTax, but more fun, that allows you to take a system and walk through the system components and then create, and I'm just going to slide ahead, I'm going to come back, create a guide that walks the owner through their system care and maintenance. And the thing that's nice about this tool is that, number one, it was developed at a national level, so it includes and incorporates technologies used all across the U.S. But along with that, it gives the owner kind of a clear, here's what I need to do for my system to help it operate, and some good tools or clues in terms of dealing with it, dealing with the process. It also allows the creator to customize it for the area, for the type and size of system. So again, this can work from a single family home to a cluster, from a septic tank to any of the advanced technologies that are out there and available, and incorporate individual pictures. So it allows you to take and customize it for the actual site or owner that you're dealing with. And that's been one of the big parts in terms of feedback that we've gotten as people have started to use the tool, that the owners really kind of feel that it's a helpful or a special tool when you incorporate pictures of their system, pictures of their house, and those type of things. The other thing that I found it to be very useful was that we found with a number of the cluster systems, and in Minnesota jargon, that means that the soil treatment area is not on the property, that a lot of those owners didn't even know where their system was or what it was. And so by incorporating some pictures of the system, by incorporating some pictures of the technology, it helped homeowners better understand that. The other thing, as a Norwegian, this tool is incredible in that right now it's free. So it is available for all of us to use. The website is the address you see on the top of the slide. So H2 and then the word and M is the website where you can go. And what you're looking at here is the beginning page of that. So the first time you use it, you register as a new user. and then afterwards you'll be coming in as an existing user. And we maintain the website. We allow, or you can create templates, so you can go ahead and work through your local neighborhoods, and you can incorporate contacts. I saw a number of you work with different organizations that you may want to be the holder of the O&M, so you could be some of the contact components as you're dealing with it. I also like that it is a place that I put the installer and the other people's contact information, so all of that is put together. And then I can customize it for the actual user. And one of the other things that a number of people have used the tool for is, instead of just a O&M guide, they've used it as a reporting component. So we've had a number of point-of-sale inspectors that have incorporated the local inspection form, and then it not only covers the inspection, and they can incorporate any pictures that happen during the inspection, but it also allows them to incorporate some O&M information for the new owner. So it's all in one document as they're working through it. So it's been a very helpful and useful tool as people are looking at that. So that's a 15-minute oversight of all the excitement that's here in Minnesota. I just again want to say thanks, and I'm looking forward to any of the questions in terms of where I spoke Minnesotan or things weren't clear in terms of how we're dealing with stuff.
Thanks, Dave. You mean Minnesotan Yader?
You betcha.
Thank you so much. And again, just a verbal reminder for folks to submit questions in the chat box, and we'll get those to Dave and then to Steve, who's going to be presenting next. So welcoming Steve Safferman from Michigan State University, and he's going to be talking about phosphorus in on-site wastewater pollutant to resource. So thank you, Steve. Take it away.
Great, thank you. Appreciate the chance to speak today and participate in the webinar. I want to recognize a lot of the contributors to this project. This has been a long-term project that I'm going to ultimately show you some results from. So basically, first I want to look at the phosphorus in general, and then the treatment techniques, and then treatment specifically to on-site, and then some novel research that we've been conducting that also includes not just treatment, but recovery. So lots of undergraduate and graduate students, as well as industry people, have been involved throughout the years with this project. And also recognizing our funding agencies. A lot of the funding has been through small business innovative research grants associated with National Science Foundation, the US EPA, and USDA. And so that's allowed us to develop some of these products and the design equations for those products. But first, let's talk about the environmental impact of phosphorus. And we've already heard about the contribution of phosphorus to eutrophication, especially in the freshwater system. And obviously, when we have eutrophication, we have taste and odor problems, especially if that water is used for drinking water, turbidity, and combined, that's going to lower the value of the waterfront property and the recreational value of that property. Also, we've been hearing a lot about phosphorus in terms of the cyanobacteria problem, so its contribution to toxic algal blooms. But on the other hand, on the positive, we need phosphorus, essential for life. There is no substitute for phosphorus. It's not like driving an automobile and that you can use electricity. Ultimately, if you have a battery storage system for your automobile, phosphorus is it. That's all we have. There's no substitution. So we often think about phosphorus as non-renewable, because once it does get into the environment, it's very hard to get it back out. And the problem is phosphorus is actually scarce. It's more scarce than oil. There's only about a handful of countries that have a lot of phosphate rock, and many of those countries are politically unstable. So here we have an element that is essential for life, but it's also a major pollutant. So obviously there's some very low discharge limits in ecologically sensitive regions, and we all think that probably the regulations on phosphorus are going to go up. But also there's a lot of motivation, encouragement to recover, to reuse that phosphorus. as we need it, it's essential for life, and there is no substitution for it. So just a couple pictures from some of the really high-profile outbreaks. So this is the Grand Lake St. Mary. This is in northwest Ohio. This is a fairly shallow lake, a very large inland lake, one of Ohio's largest inland lakes. And this has been on the news a lot because of the intense problems with blue-green algal growth in this lake. You can see by the aerial photograph that there's lots of farms around this particular lake, so lots of input from agriculture and septic systems of phosphorus into this particular lake. And these are the types of pictures that we've been seeing from that lake. So you can see that it's not particularly amenable for recreational purposes, even though there's some people using it for that purpose, but there's also been a lot of fish kills. And this has resulted in tens of millions of dollars of economic loss just for this particular area, this particular watershed. And this is an aerial photograph of Lake Erie. I think this one's from 2015, when we've had some very major outbreaks of blue-green algal contamination of Lake Erie. Even the case where Toledo had to shut down their water intakes for, I think it was 3 days, because of the toxicity associated with the blue-green algal growth. So obviously, there's lots of motivation to keep the phosphorus out of our surface water, and that motivation has been made even more critical because of the recent problems with the blue-green algal growth. So now going to the treatment of it, first we have to understand where it comes from, and this is from a particular article that really used TMDL developments studies across the country to try to estimate how do we control this phosphorus. We have to know where it's coming from first. And so obviously ag is listed as first, about 70%. Effluent from wastewater treatment plant is 5%, whereas that is probably one of the most regulated sources of phosphorus. There's only so much we can do, though, at the wastewater treatment plant. In on-site wastewater, you can see there's a big variety, 4 to 55% in a particular watershed. So that just illustrates that it's very specific on the watershed, what the contribution is, and that in some cases, on-site wastewater can substantially contribute to the phosphorus load to those surface waters. And we do expect and anticipate in the future there's probably going to be more regulatory issues associated with the phosphorus from on-site wastewater. So we're going to emphasize then on-site, but first, how do we treat phosphorus or remove it from different waste sources? And really, most of our phosphorus is either particulate or soluble, depending on the source of the phosphorus. So this, for example, animal manure probably has 90% of the phosphorus tied up in the particulate fraction. And so basically this is removed by solid liquid separation by some filtration technique or sedimentation technique. When you look at human waste, however, it's probably going to be more soluble, dissolved. And so we have other different technologies that could be applicable, including biological, where we have excessive uptake of the phosphorus by the microorganisms, and then we do use solid liquid separation to separate those microorganisms from the bulk liquid stream. We also can produce struvite, and we can precipitate it out using chemicals, or we might use some sort of absorption system. So this is generally how we get rid of phosphorus, but with on-site wastewater, it's a little bit more tricky because we don't have a system that is operated day in and day out. The system might not even be looked at for years at a time, and even an advanced system might be 3 or 6 months at a time. So that narrows down our choices for on-site wastewater applications. So to start with, we have about 10.4 milligrams per liter of phosphorus in a typical wastewater from a home, and we do get some of it out in the septic tank, so 20 to 30%, and then the rest, I guess we could consider soluble. And really the 3 ways we handle that currently include the soil absorption system, maybe some sort of reactor system, and the last is some sort of media absorption, so some more sort of engineered system. So we'll go through each of those relatively quickly, but then spend a little bit more time on the last item, the media absorption of the phosphorus. All of it's based, though, on precipitation when it comes to on-site wastewater. We don't really try to use biological because in most on-site systems, if we do accumulate extra phosphorus in the bacteria that's treating the waste, we don't remove that bacteria routinely from the system, and the phosphorus will simply just go back into solution. So no matter if we do absorption or some sort of chemical precipitation, it's all based on the precipitation of the phosphorus with metal salts, so aluminum, iron, or sometimes we see calcium. So it's just a matter of how we engineer the system to use these metal salts to actually precipitate out that phosphorus, and what do we do with the residuals. So the best way, I guess you could say, is the soil system itself, having a septic drain field where we naturally have the soils take up that phosphorus. And this is economical and can work great for 20, 30, 40 years as long as we have the right types of soils in the right conditions. Our capacity for soil is about 0.0063 to 0.501 milligrams of phosphorus per gram of soil. And the only problem is if we want to recover that phosphorus, because again, it is actually a valuable resource, can we recover it from the soil? That becomes pretty difficult to do. So this is kind of a final sink for that phosphorus. On the other hand, it's hard to beat the cost of treating the phosphorus by just using the soil system. Often, though, soil systems are not adequate to remove the phosphorus levels that we need to remove, and again, we cannot recover that phosphorus. So you see various reactor-type systems. Chemical additions of these metals is not uncommon, especially in customized systems where they might add a pump and a chemical feed system, and then precipitate the phosphorus and then take it out in the filtration system. We also see vegetation systems, living machines. So one of the most well-known living machines is at Oberlin College, where the vegetation takes up the phosphorus, but of course you do have to harvest that vegetation, otherwise the phosphorus will go back into the system when the plants decay. And this is not at all the only novel system, it's just one that I became aware of recently, is the electrochemical system, where they use iron electrodes, apply a current, and that dissolved iron then precipitates out the phosphorus that then is removed by a filter. So this is the Waterloo ECP process. And again, there's other companies that have their own commercial systems that are somehow contained in a reactor or a greenhouse or some sort of wetland system. So that's one option for on-site wastewater. And then in a sense, we do recover some of that phosphorus in the vegetation, and potentially we could recover it in the filtration process. But another way that we are looking at more recently is some sort of media, so some sort of contact system, absorption system. And these are two examples of commercially available absorption media. One is metamaterial phosphate sponge. And I'm going to talk more about that one, not because of favoritism to that company. It just happens that we have worked a lot with that company and they've supported our research. But another very similar product is the ABS Wastewater Biomass, and that's also commercially available. I think there's a few other companies that are selling such materials. And so this is now going to be more of a engineered reactor system. And so the wastewater would proceed through, usually we would put 2 columns in to get the maximum efficiency of the media, whereas it would exhaust the first column, but we'd have breakthrough at levels that would be high, that would then be polished with the second column. And then we'd always switch those columns. And this would allow us to actually recover the phosphorus if we use these external reactors. But you do see some of this media proposed to be used in situ, where it's actually part of the drain field where the water filters through the media first before going into the soil, but that makes it a little bit more difficult to recover. And so, again, I want to talk about the phosphate sponge a little bit more. So basically, this is an iron foam, which has a surface area of 15 square meters per gram, and that's the SEM photograph on the left. And then they nanocoat it, and then they bring up the surface area all the way up to 100 square meters per gram, and they nanocoat it with another iron crystal. So it ends up that this media has a tremendous amount of iron on it per gram of media. and lots of porosity, 80% porosity, and we've been able to then get up to 70 milligrams per gram of phosphorus out on this media, and again compare that to the soil, which is well below 1 milligram per gram, often below 0.5 milligrams per gram at the most. And so this again is the same concept for these other manufacturers of such materials. And so over the years, we've been experimenting with this type of media, actually a couple of different styles of the media and different types of manufacturers. The photograph on the left is our typical laboratory setup, where we've tried different types of media, different configurations of the media, different design parameters, and different waste waters. And on the right is a field demonstration. So those canisters are about 2 feet tall and 8 inches in diameter. And those are actually commercial size canisters. They would actually, one of those canisters would actually serve our home for about a year, we estimate, based on the design equations. And this is a typical graph that we would get where we'd, in this case, at this particular site, we have 7.23 milligrams going in, and we have 0.33 going out. And the retention time, empty bed retention time in those columns, so how long it takes for a particle of water to actually proceed through the column, is about an hour and a half. We can, however, increase that retention time to decrease the effluent phosphorus level. So we've been able to get down actually way below the 0.33, down to 0.1, even a little bit below 0.1, depending on how we manipulate the experimental conditions. And so again, an important part of this and kind of goes back to the first couple of slides is recovery, because even though the phosphorus is an environmental problem, but it's also valuable. And so there's a couple of ways to try to recover this type of media. I noticed that ADS media is used almost extensively just directly as a fertilizer. So this just shows some experimentation that we have done where on the left, this is lettuce that's grown with the phosphorus being exclusively from the media that was subject to on-site wastewater. And so that media then became a slow-release fertilizer, providing phosphorus to that crop. On the right was the same plant grown without the phosphorus, and not too surprisingly, it didn't do well. We did find when we compared the fertilizer, the media as a fertilizer, it was very much a delayed release. So even though the lettuce ended up looking very, very good and pretty much equivalent to lettuce grown on optimal fertilizer blends, it still took a little longer. It was a longer process to grow that crop. This was just some preliminary results. And also just in the graph below, this is some results from the material of regeneration of that phosphorus and the regeneration of that media. So to get the phosphorus out, they use a sodium hydroxide solution, and they end up using repeated washes of the media with the sodium hydroxide. And you can see which sequential washes, up to 5, you remove less and less phosphorus. And eventually you do get to the point where you cannot recover the media, and it has to be replaced. So to make it economical from a cost perspective, you do have to recover that phosphorus, and then you can reuse the media and recover the phosphorus for beneficial purposes. So that's the end of my presentation. And so again, I appreciate the opportunity to share this research with everybody, and look forward to any questions.
Great, Steve. Thank you. For those of you that are on the line with us, any questions that you have, if you can put those in the chat box on the lower left-hand side of your screen, and we'll give those to our presenters. So Steve, I guess I'll start out while we're waiting for folks and say, can you just review for us where you think this kind of system, this phosphorus recovery system, like what kind of areas would be best suited from a water quality perspective from using this kind of system?
Yes, definitely. So I think there's several different applications. Let me first start with where it would not be used. A big municipal wastewater treatment plant the biological phosphorus uptake is very, very economical and very effective. And so we probably would not employ this at that type of facility. And also, if you take those biosolids from the municipal wastewater treatment plant and use them for beneficial purpose, apply them to land for crop use, then you are, in a sense, recovering that phosphorus. So I think the applications here are for more remote sites, so sites where you don't have the operational staff that can maximize potential use of biological phosphorus removal, but in sites where you might even not have anybody looking at the facility for a year or 2 year period. So the on-site wastewater application, I think, is has a lot of potential, because you can basically put a cartridge at the site and then about once a year come back and exchange it for one that has been regenerated. We've also looked at the technology for agricultural applications. So at the end of a tile drain, for example, it gets a little bit more tricky, I think, in terms of metering the water through the column, because again, the performance of the media is greatly dependent on the empty bed contact time, so how quickly you pump it through the columns. But there's different configurations that I think could be applicable. We have not done a demonstration from the agricultural side, even though we'd like to do that and have some proposals out to try to fund such a demonstration. So right now it looks like the on-site wastewater could be a really good application for this material.
Rebecca, your microphone is not on.
Thank you, Janice. So specific, are there specific soil types or other kinds of on-site situations that this technology might be most effective for?
Yeah, so I think in general, what I've observed is that for a lot of applications, for a lot of on-site wastewater treatment systems that are not close to surface water, and the groundwater is quite deep and not directly immediately connected hydraulically to surface water, I think a soil system works very well. There's certain characteristics of soil, depending on the metals, the clay contents, that has higher capacity than other types of soil. So I think the application here is going to be for more advanced systems where you have environmentally sensitive regions where you might have homes along a lake, for example. You might not have you might have a lot of rock material and a lot of sand instead of good soil, kind of good organic soil and soil with minerals in it that it might not take up a lot of phosphorus. I think those are all applications for either an engineered product, a media product, or even some sort of waste iron slag that you might just mix in the soil at the point of disposal. So we really envision this engineered media being as part of already an advanced system that uses reactors and that we can monitor. So this would just be another basically manhole that would contain the media where the water would pass through before it's being discharged.
Great, thank you.
Another application for this would be the systems that don't use soil. You know, I saw the picture of Ohio. There's a large number of those systems that discharge directly to the surface coming through a aerobic treatment unit or maybe even a shallow sand filter. Those systems in particular, any phosphorus that's in the wastewater ends up getting into the environment, into the surface water potentially. So those systems would be another application for the phosphorus recovery.
Thank you, Dave. Okay, other questions from participants? Again, looking for those in the chat box. And while we're giving people more opportunities for that, I'll just ask Dave a question. So Dave, any other tips that you would give folks from other states related to the H2O&M system, like how it sounded like it was adaptable for various different places, but can you be more specific for other states about what kinds of things we ought to be thinking of if we're interested in adapting H2O&M for our states?
Yeah, so first off, it was written by a national group so that we tried to create national appeal in that any of the technologies that were being used were incorporated into the tool. Now, the first time through, there may be technologies that don't apply to your neighborhood, so you would make a template getting rid of the technologies that you're not using. And that would then make it easier the next time that you're using it. So step one is to make it yours so that it would work well, and then be able to adopt and go through it. The other part of adaptability is that you could incorporate any of your kind of code and standards, so things that you felt were important. So for example, with holding tanks, if you had a reporting requirement, you could incorporate that into the tool so that people would be able to have the reporting requirements right in front of them. And then the updating in terms of phone numbers and those kind of things also make it locally helpful.
Okay, great, thank you. And Steve, how long till you envision that this type of technology is available for installation across the region?
So my understanding is that it is available already. So both ADS is commercially available, and the metamaterial is already available. So both are available, and I believe there's a couple more companies, but they're not really coming up. When I did a quick search before the presentation, that do have some sort of media. There's also been a lot of custom type. I shouldn't say a lot, but I've seen some examples of engineers designing some sort of waste slag, iron slag, with some waste materials and putting that into some sort of reactor system and using that to uptake the phosphorus. So it seems like it's already available, and I don't think it's been used extensively yet, and that's kind of I think one of the challenges, because to really get the full benefit of using engineered material, you do have to recover it and regenerate it. But to do that, you need enough of a usage of it and enough business to make it worthwhile. And it has to be somewhat regional, otherwise it's going to be expensive shipping canisters all over the country. So at this point, I think it's ready for use. We ourselves have done a lot of testing of it for over. I've actually been working over 10 years on testing these types of medias of different generation. It seems to be ready, but I think some of it's more of a business type challenge than a technical challenge.
Okay, and you may not know the answer to this question, but you're showing the recovered phosphorus being used to grow food that people would eat. And are there any concerns that you're aware of for using this recovered? I mean, it looks like they're just extracting the phosphorus from the media, but is there any concerns with contamination of the phosphorus, or anything else with use of the recovered phosphorus that we should be aware of?
Yeah, I think that's a really interesting and very good question. And the other concern is also that the material from metamaterial is a nano-coated material. So there's a question about any nanoparticle release into the environment. And so that's something that I personally thought about. And at one time, we did actually try to nanocoat some other materials as a disinfectant onto the media, but quickly discontinued those experiments just because of your question leads to the concern that if you do release nanoparticles of silver, for example, into the environment, that could be a health risk. So we're not aware of issues associated with iron nanoparticles if they do release. Although I guess there is some literature, and I don't follow this literature, but some concerns that nanoparticles themselves could just physically get into cells because of their small size. So I think that's an area that needs some more research. I don't think growing a crop on it necessarily would be an issue, but I think there's probably a little bit more work to do on making sure that the release of any nano iron particles into the environment, make sure that's not a particular harm.
Okay, great. So any last chance for questions, and then any parting words of wisdom from our presenters before we adjourn? Okay, no additional questions. Dave or Steve, any parting comments from you?
This is Dave, and I have limited wisdom, but I will say that if people have questions about any of those on-site topics, then I'm more than willing to talk with people or work through those type of things with people, so I'm more than willing to do that. There's my contact information, and I enjoy talking with people in different neighborhoods. I guess the last thing I will say is that our state regulations are what really have facilitated some of that connectivity, and so and if you would like to talk about those type of things, I'm more than willing to talk about those. But thanks a lot for investing some time this afternoon.
Well, thanks to you both for your leadership. And Steve, any parting comments from you?
I also would echo what Dave has said, and definitely please contact me if I can answer any questions, or if you want to look into a demonstration. And the only other thing I could offer is, when we think about some of these pollutants, I think we should also think about them as resources, and that's absolutely true with phosphorus. So the opportunity to solve an environmental issue, to solve a water quality issue, and then recover a viable resource like phosphorus, I think is a win-win circumstance. So I think we should continue to try to research and test and demonstrate technologies to change the waste back into a resource. Great.
Thank you, Steve. And Sharon, yes, we do make the presentations available we archive the presentation recordings, and those will be available on our website, and we have and also on eExtension, eExtension's website at learn.eextension.org. You can see that at the bottom of this slide. And Sharon, if you need the PowerPoints or PDFs of the PowerPoints, just send me an email, and we will see if we can get those from our presenters. And I'm putting my email in the box there. There you go. Thank you all for joining us today. Our next session these are always on the third Wednesday of every month at 2 p.m. Central, 3 p.m. Eastern. So April 19th is our next one. We'll be talking about nitrogen management in tile-drained landscapes. And Laura Christensen from the University of Illinois, Jane Frankenberger from Purdue University, and Chris Hay, formerly at South Dakota State University and currently at the Iowa Soybean Association, will be presenting. And we've got a great new publication that Laura has led, and many folks have contributed to, 10 ways to reduce nutrient loss and nitrogen loss in tile-drained landscapes. So I know that's part of what they will be covering. So thanks again, everyone. Appreciate you joining us, and have a great rest of the afternoon.